My dear students, last lecture we complete the portion of a permutations group, alternating groups, and we have to discuss the d ideals group. Now, this lecture today we start the first define the coset, and then we have to discuss if we have some examples. If we have a time, we have to discuss the properties of some property of a coset. So, let us start with the definition of a coset. Let G be a group and H be a subgroup of a G. Then for any G belongs to G, the set HG as the H is the element of a H is called the right coset of H in G containing G. Analogously, we can define the left coset as a GH. GH is the element of a H is called the left coset of H in G containing the containing G. So, we have a H, first we have a subgroup of a G, and we have any element of a G is the element of a G. Then simply we can say that the HG is a right coset. If the element of a this is a HG type, this H is the element of a H, and then similarly we can say that G of H is equal to, we have a G times of a H such that H is the element of H. So, these are the elements of a, this is called the clearly is a left cosets and the right coset in the similar fashion. So, right and left cosets of H are the subset of a G. So, when group written additively, we can write the cosets in place of a this. If we have a this can be written as a G plus H or H plus G types like this. We have to write H plus G, H plus G, H is the element of a G, is a binary operation, is addition, and then we have a G of H and the right and the left cosets of H respectively if the group is written is a additively under addition. This satisfy this condition. And if you just see that a right coset is not necessarily a left coset and a left coset not necessarily is a right coset. But when you have a group is a commutative group, then however when a group is commutative, the right and the left coset are coincide, and is evident that the from the definition, if this because we have to just say that G is a commutative, then HG can be written as a G of H, because G group is a commutative, then this G is the element of a G, and if G is the element of a G, then G can be commute every element of a G, and H is the clearly the subset of a G. So, all the elements of this means clearly H of G can be written as a G of S, then the left coset is the same as the right coset, and right coset is the same as a left coset. So, we can simply say that whenever in general the right coset is not the same as the left coset and left coset is not the same as the right coset, but whenever group is abelian, then we can say that right and left cosets are coincide, and then by the definition this is very clear, we can say by this hold into this form. So, let us a very trivial example, we take a clearly set of integers and then we have to take a 2z. So, we take any element of a G. So, we have a 0 is the element of a Z, then we can, because this is a group under addition. So, 0 plus H is equal to, you can say that if you have a H is equal to the element of a this is equal to H is the element of a 0, and then you have a 2, 4, 6, and then you have a plus minus and so on. So, this can be written as a 0 plus 0 is equal to 0, 0 plus minus 2 is equal to plus minus 2. This can be written as 0 plus 0, 0 plus minus 2 and so on, and that is nothing but is equal to 0 plus minus 2 plus minus 4 and so on, and that is equal to again H. So, whenever we have to writing the 0 plus H is equal to, you have a H. Now, another element for a 1 is the element of a Z, then if we write a 1 plus H is a coset. So, we have to write a 1 plus 0 is equal to 1, and then we have to starting from this 1, and then you have a 1 plus H and then you have it write in the form of all the elements of this H into this form. So this is clearly you write in the form of a 1, and then next is equal to 3, and then you have a 5, 7, and then you can just put a write into this form. So this is clearly we have to write into this form. If we write it 2 plus H, then this is again giving you the same as a H, and then if you have a 3 plus H is again give him a same as a 1 plus H, and then we have to write into this one. So clearly this H is a subgroup. So let us find the right cosets of H in G. These are all the set of the form of a H plus G, where G is the element of a G. So we see that H plus 0 can be written in the form of 0, 2, 4, and then minus 2, minus 4, and that is clearly H. Then 1 plus H can be written as a 1, minus 1, 3, 5, minus 3, minus 5 in this form. And then if you write a 2 plus H, this can be written as a, this is equal to 2 plus H is equal to, you have a this form, minus 2 plus 2 is equal to 0, and 0 plus 2 is equal to 2, 2 plus 2 is equal to 4, and so on. If we write as 3 plus H, and this is equal to, you have a 3 minus 3 is equal to, you have a 0, 3, and then we have to write as a 3 plus 1 is equal to, you have a 4, and then so on into this form you can write in this form. So in general H plus G is a even integer in the form of a this coming into this. If H is an odd integer, then every time is coming into a this form. So here just so you can see, if you want you can just write into form of this one more. Suppose we have to write a 3 plus H is equal to in the form of this, then you have to write 3 plus 0 is equal to, you have a 3, 3 plus minus 2 is equal to, you have a 1, and 3 plus minus 4 is equal to minus 1, and then 3 plus 2 is equal to, you have a 5, and then you can see this is similarly this is the same as a 1 plus H form. So if we write is a 4 plus H, it is again giving the same H. So in general we can say that if we have a this G is any even integer, then H plus G is in the form of a H, and whenever G is any odd integer, then H plus G can be written as a H plus 1. So that means we have only two distinct right cosets of this set of G is equal to, we have a set of integer under addition, and H is equal to set of a even integer under additions. So we have only two distinct, so thus this is only two distinct right cosets of H in G. Also has two distinct left cosets of H in G. Similar fashion we can just write in place of a H plus 0 is giving H plus 1, and then we have a take H plus 2 is equal to again H, and H plus 3 is again you have a same as H plus 1, and the similar fashion we can say that if is even, then you have a H, if G is odd, so this is 1 plus H plus 1 in this form. So there is only two distinct right cosets of H in G, and also two distinct left cosets of H in G, and they are the same because group is abelian. Same as the right cosets, because we have to just say that if a group is abelian, then we can say that the right coset and the left cosets are the same. So in this case we can simply say that we have these two cosets are the same, and they are only two distinct cosets are there. So there are only the cosets of H are H plus 0 and H plus 1, or we have a 0 plus H or 0 plus 1, and then H plus H is H plus 0 is equal to H, of course subgroup of a, and this is a subgroup of a G. H is a subgroup of a G, but this H1 H plus 1 is not a subgroup of this G, because you know that H plus 1 is the element does not has a identity element, because H plus 1, the element of H plus 1 is equal to 1 minus 1 and then 3 5 minus 3 and so on, but there is does not exist 0 does not belongs to the H plus 1. So this means clearly H plus 1 does not possess the identity element. So if this H plus 1 does not possess the identity element, then we clearly say that this H plus 1 is not a subgroup of a G. In fact, we simply say that H plus 1 is a set of all odd integers. We have to just say that this is a set of all odd integers. So H plus 1 is simply the set of all odd integers, but there is only two distinct right or left coset, because we have a group is abelian. So if group is abelian, we can simply say that we have only two distinct cosets here. So another observation, if you see, because H plus 0 and H plus 1, then we have a 2Z and 2Z plus 1. So if you take a union of these two, you getting the, if you take a union of a 2Z and the union of a 2Z plus 1, then you getting the Z. And you see, if you take a intersection of these two, 2Z plus 1, then you getting the empty set. So that means G can be partitioned into that means the our group, the Z, clearly this you have a Z is a 2Z union 2Z plus 1, and then you can say that this union is equal to, you have giving the whole set G, H plus 0 and H plus 1 union is equal to G. So G is equal to Z is a partitioned into these cosets. So and then you can say clearly the intersection of these two are empty. So in general, we can, this observation we have to just say that means we have this collection of all the left cosets. If you take a union of the left or right cosets, whatever this, so if you have take a collection of all the cosets, that is giving the is equal to giving the G, and if you take intersection, that is clearly giving the empty set is there. So now another example, suppose for example we take a K4, I have discussed so many times this K4 group, Klein 4 group, and order of A, order of B is equal to 2 and AB is equal to BA, because you know that we have to just say that is a third. I just take a, in place of a C, I put a and B, because AB is equal to C, we have to put in, and AB and BA are the same. So we take a H is equal to this E and A, and clearly this is a coset, because if you take a element of a E, this is a group under multiplications. So we just say that H into E is equal to H. So if you have a H into E is equal to, you have a E, and to A into E is equal to A, this is equal to H. And now if you take a H of A, then H of A is equal to A into sorry, H of A, so E into A and A into A, identity into A is equal to A. So then A square, and A square is again you have a order of this, so A square is equal to identity. So this is again H, and then we have to just say that we have to calculate about the this H of AB. Now H of AB, H of B is equal to, you have just said that B into AB. So we have another element is equal to B, then we have to check is H of AB, and now H of AB can be written as a AB and A square B, A square is equal to A, so AB into B is equal to AB. So we have to HB, so we can say that this again we have a H, and we have to H and H B are the two distincts. So there are exactly two cosets of H in K, H and HB, and the same as a BH, because this again group is abelian. So left coset and right coset are the same. And then if you take a union of these two, H union HB, then you can see clearly you getting the K4. And if you take a H intersection HB, there means you clearly getting the empty set is there. So this example is also very clear. So we just say that is very clear. That means if you again we have to getting the two cosets, and these two cosets are again this group can be partitioned into the group of the coset. This means we have exactly two distinct cosets are there, H and HB. If we take a union of these two is generated by whole set K4. If we take an intersection, then clearly we have this empty set. Now another example for discussing this, U8 is equal to this, and this is clearly is a group under multiplication of modulo add. We have to write H into 1, element of a G is equal to 1. So this is H1 is equal to 1 into 1 and 3 into 1, and then clearly is equal to 1 and 3, and this is equal to H. Now we have to write H3, then we have a 1 into 3 and then 3 into 3, and then 1 into 3 is equal to you have a 3, and 3 into 3 is equal to you have a 9, and 9 you have to take a under multiplication modulo 8, and then this is equal to 1, then this is again you have a, this can be written 1 into 3, again you have H. Now we have to take the H 5, then you have a 1 into 5 and 3 into 5, then 1 into 5 you have a 5, and then you have a 5 3 is 15, and divide by 8 you getting the 7. So this is clearly H5. Now H of 7 we have to calculating 1 into 7, and then you have a 3 into 7, then you have a 7 and into 21, and then 21 and divide by 8, 16 is remainder is equal to 5, and this is equal to H5. So in this case we also say that clearly there are two distinct again we have a, there is only two possible H and H5 are the two distinct cosets are there, and these coset, if you again take a H union H5, then you can say that you can take in the G, and H intersection H5 is clearly you have a empty set there. So by this example we can also say that this 1H is equal to this, 3H is equal to we have a H again, 5H is a 7H is again we have to getting the 5H there. So there is again we have a H and 5H are the H and 5H are the only two distinct left cosets of H, because one of H this is 1H and 3H are the same, and 5H and 7H are the same. So generally we have to say in this case we have to these two are the distinct cosets of this. So now observe that again H and 5H form a partition of a G, and also observe that 5Z is not a this clearly 5Z is not a subgroup, because again identity element is not here. So this is 5H clearly is not a subgroup of a G, but this clearly 1H is a H is already is a subgroup. So this coset is again form a partition of a G, and this thing. Suppose we have to take this interesting one, we take an example of one example for this S3, and S3 we have to just take a element of S3. You know that I just write in the cyclic notation, this is a 1, then you have a 3 of order 2, and then 2 of order 3 permutations are there. So this is 1 2 2 3 1 3 1 2 3 and 1 3 2. And now we take a subgroup of this H is equal to, we have to take a 1 into 3. We can also take some H1 is equal to in the form of a 1, and we have to take a 1 in place of a 1 2, we take a 1 2. Now clearly this is a subgroup of this H, because this satisfies the properties of a group, because it's a close, because 1 3 and you have a 1 3 is equal to identity, and then 1 into 1 3 is equal to 1 1 3. So is a closed, and 1 3 is a inverse of a if you have a if you write the inverse of a 1 3, then you know that 1 3 inverse is the same as a 3 1, and then 3 1 can be also 1 3. So inverse of this 1 3 as a itself, 1 is identity. So clearly this S is a subgroup of a S3. Now we find all the cosets of this. So we just write 1h, 1h is equal to h, we have a permutation multiplied by this. Now we have a 1 2 h, so 1 2 with 1 2 is multiplied by identity, then we have a simply is equal to 1 2, and then if we take 1 2 multiplied by 1 3, then we have a 3 goes to 3, so 1 goes to 3 and 3 goes to 1 and 1 goes to 2 and 2 goes to 2, 2 goes to 1, then it's closed. So this is equal to, in place of this product of these two is equal to 1 3 2, and then this is nothing but is equal to, you just check, this is the same as a 1 3 2 into h. So we just write if 132 into h. So if we write 132 into 1 3, if you write 132 is 1 3. So if you write 1 3, so yes, 1 goes to 3 and then 1 goes to 3 and 3 goes to 2, and then you have a 2 goes to 2 and 2 goes to 1, then is equal to 1 2 is here. So you getting the 1 2, and if you have multiplied by this, you getting the this. So clearly we can say that the product of these two we have to write in the form of a this. Clearly you have just said that we have to this h is equal to, if we have to write in the, so in the form of this, in place of a 1 3 2 h, and that is giving the same of this element. Similarly, we have to start from the 1 3 h, and the 1 3 h you just check. If you take a 1 3 h, you have a 1 3, and then you have to 1 3 1 3 is equal to identity, then you have again getting the h. And if we have to calculating 1 2 1 and 1 3, now we have a 2 3. 2 3 h is equal to 2 3, and then 2 3 and to 1 3. So this is 1 goes to 3. So this means can say 1 goes to 3, 3 goes to 2, and then we have a 2 goes to 2, 2 goes to 3, then 3 goes to 1, 1 goes to 1, and then 1 2 3. And now we have to check this is this form, and now we have to calculating the 1 2 3. So 1 2 3 h, and then you have a multiplied by identity, you have a simply this simply you can say that 1 2 3, and then you have a 1 2 3 was 1 3, write this 1 goes to 3 and 3 goes to 1. So 1 is clear. Then we have a move to the next element, 2 2 goes to 2, 2 goes to 3, and 2 goes to 3 and 3 goes to 1. So similarly we have to write in the form of this, clearly giving us a 2 3. So we have to write a product of these two. This is clearly this we have to write into the form of a this is equal to 1 2 3, then 1 3, this is equal to 2 3. So this is common clearly. So this is a 2 3. So this means this is equal to 2 3, and this is the same as a 2 3 h, and then we have to write this thing. So this means we have a clearly. Now you just check we have a these two 1 2 h, and this is the same, 2 h is the same. Now we have a these two are the same. So we have a clearly we have a 3 different left cosets of h in GR, h 1 2 h and 2 3 h. There is a 3 different 3 cosets are there. So clearly we have these 3, and now if we take a h 1 2 h and h are disjoint, clearly intersection of these two is empty, intersection of these two is empty, intersection of these two is empty, and then if you take a union of these, all this is equal to, you have to giving the S3. So we have clearly we have to show that that means clearly this again this is a partitioned, all the coset is partitioned of this S3 in the form of h 1 2 h and 2 3 h. So clearly we show that that means these are the in this S3 h is equal to, we have a 1 3. So we have to these are the permutation. Now I just leave for this, you have a try for if H is equal to, you have a identity and 1 2, and then check if it is, because again if you taking this, you have to taking the uh, elements of this is a form of a disjoint cycles or not. In general, now we have to remark this. Now you see that in general GH and HG are not the same as the previous example. 2 3 H is equal to, you have a 2 3 1 2 3, and then you have to just check we have a H. If we have to multiply it, H is equal to in this way, then we have a 2 3 bus 1 3 and 2 3, and 1 3 2 is equal to you have 1 goes to 1 1 goes to 3, then we have a 3 goes to 2 2 goes to 2. So we have a 1 3. So if we take 1 3 and you have a 2 3, this is equal to 1 3 2, simply 1 goes to 1. So 1 goes to 1, 1 goes to 3, 3 goes to 2, and 2 goes to 2, and 2 goes to 3, and 3 goes to 1. So this means you have a clearly we have a 1 2 3, but in this case we have a this is equal to 1 2 3, and this means this is clearly is not the same. So we have a provide a one example where we say that the left cosets and the right cosets are the different. So in this case we can say that in general left and the right cosets are not the three, because you can see if the previous all the examples we have to show that the left and right cosets are the same due to the abelianness, because the we have to choosing the groups are abelian. But you know that already this S3 is a non-abelian group. If S3 is a non-abelian group, then we have to show that clearly this left and right cosets are not the same. So in general we can say that left coset and right coset are not the same, but only in the case we have a if we have a groups are the abelian groups. So now I just define one more definition of a congruent modulo n we have to define. Now we have to define the congruent to modulo of this subgroup. Let G be a group and H a subgroup if A and B are the element of H. So we say that A is a congruent to B modulo H, and we write A congruent to B mod of H if A inverse B is the element of H. So we simply say that, means simply say that A is congruent to B over mod H, then if A inverse B is the element of H. So in the case of additivity, we can say that A inverse means we have can say the minus A plus B is the element of H. Means inverse of A is inverse of A. You know that if we have it as a mod of H, then H should divide the B minus A and A minus B, whatever this, and then in the general congruent, if we take A congruent to B mod of N, then N should divides B minus A. But here we can say that because H is a subgroup, so we can say that minus A means the inverse of this element. So we simply say that A congruent to B mod H is only say that if A inverse B is the element of this set H. So now we just said that, for example, we have to just say that let G be a group of set of integer and H is a multiple of a 7. This is a subgroups. Then we take a minus 1 plus 22 is equal to we have a, because the group is under addition, and then we have a inverse of a 1 is a minus 1. So minus 1 plus this, you have a H is equal to what? H is the element of a you have a 0 7 7 we have a 7 plus 7 and so on, so like this 7 14, then we have a 21 and so on like this, and similarly we have to go to the minus plus minus plus minus plus minus, all these things happen. Now just check. Okay, so we have to write into this H is the element of this form, and now clearly you just see minus 1 plus 21 is equal to 21, and then 21 is the element of H. This means we can say that these two are congruent to 1 is congruent to 22 of mod of H. Mod of H means you have a 7Z. So clearly 1 is congruent to 22 mod of H, and in this particular case the notation is identical to congruence modulo 7. because we have to, in general we have a multiples of a 7. So this 21 minus 1 is 7, so 7 should divide the 21. So in this case we can say that simply this is a particular case, the notion of identical to the congruent modulo 7. Suppose we take another group, another example. Let G is equal to, we have a G20, and now G is equal to U20, and now you know that the element of a U20 which are relatively prime to 20, 1, 3, 7, 9, 11, 13, 17 and 19 are the element of this. Now we have to take a H is group generated by 7. If it's generated by 7, you have a 7, and then 7 to the power 1, then 7 to the square, then you have a 49, and then you have a divided by this is equal to, you have a 9, and then you have a 7 to the power 3, then 63 divided by the 20 is equal to, you have a 3, and then we have a 7 to the power 4, 21 divided by 20 is equal to 1, and then we have a 7 to the power 5 is equal to, you have again 7, is repetition is start. So that means we can say that, so H is only this, the 4 elements are there. So 1, 3, 7 and 7 square. So F is generated by 7. So 7 to the power 1, 7 square is 9, 7 to the power 3 is equal to 3, 7 to the power 4 is equal to identity. So 7 to the power 1 is equal to 1. So if H is generated by 7, then clearly this 1, 3, 7, 9, and this is clearly, you have to just check if you have a 1, 3, 7, 9 under multiplication modulo 20, this is a form a group. Okay, so this is clearly is a group. So you have to take all the element is closed, and one is the identity elements and inverse of each element. So this, if you take a 3 into 7, 3 and 7 are the inverse of each other, and 9 into 9 is the inverse of itself, 1 is only inverse of itself. So every element has a inverse. Now we take as 13 inverse into 7, 19, this is the same as a inverse of a 13 is a 17 into 19, and that is equal to 3, and 3 is the element of H. That means we can say that 13 and 19 are congruent to H. So 13 and 19 are congruent to each other, and that is the congruent to mod of H. So we can simply say that this is way we can say that if 13 inverse into 19 is equal to, we have to getting the 3 inverse of a 13 in this group, we have a 17. You can just check if we have a this is giving the 13 into this is 17 is giving identity is element in this case is equal to 1. So this means the inverse of a 13 is equal to 17. So we have a 13 inverse 19, 17 into 3, and if 17 into 19 multiplied by this is divided by 20, remainder is equal to 3. So we can get, if you multiply these two, getting the remainder is equal to 1. So this means 13 and 19, 13 congruent to 19 mod of H. So this way we can define. In the next class, I have to stop this class to here, and we have to, in the next class we have to discuss the some properties of this coset, and then first we show that this congruent modulo is an equivalence relation, and this A congruent to B of mod of H if H is a subgroup, and G, and we show that this is the relation where A inverse B is the element of H. This relation is an equivalence relation, and then we continue in this direction for this further. So today's lecture I stop here. Thank you very much.